So back to this page. This is the non-Euclid page, short for non-Euclidean geometry. And what we've got here is we've got an interactive version of the Poincare disk map or model of the hyperbolic plane. And so all of these curves that you see here are hyperbolic straight segments. They are shortest paths according to the hyperbolic distance function. And so that hyperbolic distance function, that's pretty complicated. It has a lot of exponentials in it. One of the ways of figuring out a hyperbolic distance uses arc hyperbolic sines, and another way uses logarithms. So we're not going to spend a long time on where this comes from, but there's formulas out there that will let you measure the distance between points, and there's formulas out there for figuring out the length of a curve. It's, one of the calculus sorts of things. I am going to integrate along this curve to find its arc length. But there's a hyperbolic geometry version of that for the Poincare disk. And we're going to play with it here because this is really nice, and this website does all of the messy hyperbolic sine things for us. So I am going to use some of these tools here, and the first thing I'm going to do is clear everything out, and I'm going to make a line segment. So this is going to be a segment that's going to go through 2 points on the Poincare disk, and I'm just going to move around those points, and we're going to see what happens. So as I drag them towards the edge of the Poincare disk, and of course if I drag them outside the disk, then they wouldn't live in the map anymore. All right, so that's not part of the hyperbolic plane. You can only go so far and then it stops. But you can see that where it would stop, I hope that if you imagine a tangent line going along this circle and a tangent line going along this arc of a circle, those tangent lines are going to be perpendicular. So every hyperbolic infinite line, so this is now an infinite line because I took it all the way out to the boundary. This hyperbolic infinite line, maybe I should, nope, I'm going to leave it. Not going to worry about it. That if we imagine this going all the way out to the boundary, which it looks like it does, then you've got an infinite and indefinite line. If you were to use any of those formulas for distances, you would get an infinite distance from here to there. You'd be dividing by 0. If you took a limit, your limit would tell you that it was an infinite length. And all of these hyperbolic lines meet the edge of the hyperbolic of the Poincare disk at right angles, at a 90-degree angle. So I'm just going to take one of these endpoints and I'm going to move it around here. And you can see that when they get close together, it almost looks like a half circle sitting there as the shortest distance. And then my circles get broader and broader and less curvy. And if you were able to get exactly diametrically opposite points, it would straighten out to be a straight line. So it's straight if it goes through the center of the Poincare disk. And so as I go around here, then it starts to curve the other way. All right, let's look at some tools of things you can do in here. So one thing you can do is you can measure distances, you can measure angles, And you can measure a triangle, which tells you all of the angles and distances and stuff. So I'm going to start off by measuring the distance along this hyperbolic segment. So going from there to there. There's my distance. I'm going to move this around. So here it says that the distance from A to B is 2.5. All right, 2.5, whatever that is. And I'm going to move this point out towards the edge of the disc, and it gets significantly bigger, 7.48. Now I said that was infinitely far, but of course the computer is kind of restricted to pixels. All right, so part of the distance formula, you are dividing by the distance from that point to the edge of the circle. And if you divide by smaller and smaller and smaller distances to the edge of the circle, then you are getting a greater and greater output. So that's what takes it off to infinity, is this distance formula involves a divide by the distance from the point to the edge of the disk. But the computer can only go so far, and at some point it runs out of pixels, and so it looks like the longest you can actually make on this particular version is about, oh, we got 10, 11, maybe 12 or so. So, you know, you can tell at points where, you know, the computer is letting it get closer and closer to the edge, and then your distances get larger. So this is going to tell you distances. It's not going to be perfect, but it's going to be a good approximation. And get this, you don't have to do the logarithms and the arc sines. Sorry, not arc sines, arc hyperbolic sines. Okay, let's do some lengths. So not lengths, let's do an angle. So I'm going to make this AB into an angle. So I'm going to put on another segment that's going to go from A to C. And now I'm going to measure the angle. So as always, when you're measuring an angle, you start with one point, and then you go to the vertex of the angle, and then out to the point on the other ray, and that tells you the angle. And angles are preserved. So if you were to draw a tangent line to both of these curves and measure that angle between the tangent lines, you should come up with about 42 degrees. And if you went to the hyperbolic plane that this is a map of, and you drew out these same segments on the hyperbolic plane that this is the map of, you would also get about 42 degrees. So that's why I like this model of the hyperbolic plane. I like it because it preserves angles. Also because it's nice and symmetric. It's nice and round. Lots of symmetry there. Okay, so you notice when I take that point and I move it way close to the edge of the circle, of the disc, that's getting really, really narrow. So that angle is going to approach 0 degrees. Here the angle is less than 0.1 degrees. If I make a triangle, an angle that's kind of near the middle, then I'm going to get a larger number of degrees. I can get any angle between 0 and 180. This program always measures the smaller of the two angles, so it's not going to tell you the angle around the outside.